In this video, I will show you in a dynamic way how a charged object polarizes a conductor, a conducting object. Now, in this discussion, I will include both electric forces and electric fields, and also I will discuss the polarization process of the conductor. So this is challenging material. Now, as I said, this is a rod and it has a negative charge on it. Now, this is my conducting object. So this is my conductor and it is neutral. And I have done because I'm gonna show you what happens in a dynamic way. I've drawn the same picture several times. This will be at different moments in time. So let's say this will be at t equals 0. So this will be at t equals 0. This will be at t1 a little bit later. This will be at t2, and this will be even later. Now, this let's use, I'm gonna use blue for the electric field. So at t equals 0, when I bring the charged rod near my conductor, okay, at the center of the conductor, how many electric fields do I have? Well, at this point, there is no charge separation in the conducting object. All nuclei have their electrons nearby, and that means that nothing in the conductor creates an electric field, but the charged object will create an electric field at this location. And because this has a negative charge, I know that the electric field, this is the electric field from the rod at the center of my conductor, let's say C, from the rod on the conductor. This is the electric field. And because there is only one electric field at this point, E net, the net electric field at the conductor is simply the one that I have from the rod. Now, at this moment in time, I know that I have mobile electrons free to go anywhere in this conducting object. Now, because the electric field points to the left, and from theory, I know that F equals QE, for my mobile electron, if the net electric field points to the left, and my electrons have a negative charge, that means the electric force on those mobile electrons will point to the right. So a little bit after t equals 0, my mobile electrons are going to start moving to the right. And they will keep moving until they encounter the surface, the boundary of the object, and they're going to stop there. So let's say I have been able at T1, I now have one mobile electron that has left a positively charged atomic core on the other side, and I have one minus sign, one plus sign. Okay, only one, because I have not waited long enough. Now, I want to think what happens to the electric field. Well, the rod is still here. I'm not moving that around. So whatever I had before, I have the same electric field here. Again, this is the electric field from the rod on the conductor. However, something changed though. In the conductor, I now have a negative charge here and a positive charge here. And this is why I now have a tiny electric field. Let's make it a little bit bigger. An electric field from the negative side of the conductor, created at the center of the conductor, and this points to the right because this is a negative charge. In the same way, I have a positive charge here. This creates an electric field pointing away from it. And this is the electric field that the positive side makes at the center of the conductor. So now E net is not the same as what it was before. It is the sum, of course, the sum of all electric fields, the one created by the rod, plus the one created by the negative side of the conductor, plus the one created by the positive side of the conductor. And if you add all of these together, you don't get the same net electric field that you got before. If you see here, I continue to have a long arrow to the left, but now I have two short arrows to the right. And if you add everything together, you get a smaller net electric field as you did before. Now, the net electric field continues to point to the left, and for an electron in the interior of the conductor, because they have a negative charge, Q times E net points to the left, times the negative charge for the mobile electron. I continue to have the force on the mobile electron pointing to the right. And that's why I will continue to have mobile electrons moving to the right. They continue to shift. I should not have done them here. Because they continue moving to the right, at T2 I will have more. And remember, I have not moving the charged rod around, so I continue to have the same electric field that the rod creates at the center of the conductor, but now the electric fields from the negative side of the conductor and the electric fields from the positive side of the conductor have grown longer. Those are bigger. Now those are bigger electric fields. And E net, as before, E net is the sum of all of those. The electric field from the rod at the center of the conductor plus the electric field from the negative side of the conductor at the center of the conductor plus the electric field from the positive side of the conductor at the center of the conductor. And now, because these are longer, my net electric field now is smaller. Okay, so you can see the trend here. You start with a large net electric field, and then it gets smaller, and then it gets even smaller as time goes by. But the net electric field, even though it is small, it still points to the left, which means an electric force on the mobile electrons here will continue to point to the right. And that is why I continue to have mobile electrons accumulating to the right. But now, at this moment in time, I have finally reached the point where this is the electric field the rod creates at the center. I now have electric fields from the two sides of the conductor that completely counteract the electric field from the rod. So this is from the negative side at the center, and this is from the positive side at the center. So now again, E net is the sum of all electric fields. So the one created by the rod at the center of the conductor plus the electric field created by the negative side of the conductor at the center plus the one created from the positive side of the conductor at the center of that object. Now, because these have grown even longer, they are stronger electric fields. If you add them together, you get these two to completely cancel out the electric field from the rod. And at this point, the net electric field is completely zero. If the net electric field is completely zero, then this means that there is no electric force acting on the mobile electrons anymore. No electric force. The mobile electrons that are present in the conducting object do not feel a force anymore. At this point, the net electric field is zero, no electric force, no more mobile electrons will be pushed to the right. It's done. The process is over. Polarization at this point, the polarization stops, and that's because now the polarization of the conductor has completely cancelled out the electric field from the rod inside the conductor. Now, as you can see, starting at t equals 0, I start with a strong net electric field inside the conductor, a smaller net electric field, even smaller, and then it gets to 0. This is a very important property of conductors in equilibrium. Anytime, and I will write it here, anytime you have a conductor in equilibrium, like I have now at the end, I know that the net electric field inside will need to be 0. This is an extremely important property of conductors. Always true. Conductor in equilibrium, E net is 0. Is it always E net equals 0 for conductors? No. They have to be in equilibrium. You noticed at t equals 0, t1, t2, the net electric field inside is not 0. So, not always true for conductors that conductors have E net is 0. They have to be in equilibrium. And this process, now you say, how much time do I have to wait for the polarization to stop? We're talking about 1 nanosecond, okay? So this process is going to be done in 10 to minus 9 seconds or so, okay? So it is a process that you cannot really observe experimentally with your senses, with your eyes, because it's just so fast. But it does last some period of time.